Optimize. A Journey Through Database Query Optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
Today, we've gone through discussing like a bunch of variations of different approaches regarding the optimizer, whether it's going to be a top-down search, this is a bottom-up search. And so at this point in the semester now, we're going to switch to finish off some last thing we want to care about, like in the actual optimizer search strategy, how to handle unnested queries or unnested correlated subqueries. And then on next week, again, we'll see what this is in this end. Now again, we're talking about this other major part of the optimizer we haven't discussed yet. And that's the cost model piece. So today's sort of the last lecture we'll do on search strategies, at least for the canonical implementation. Then we'll build on cost models, and then we'll go through looking at some other adaptive techniques to do that. But before we get that, again, as I said, last class was talking about how to parallelize when you have transformations in a top-down optimizer, and that was coming after we discussed how to do parallelization in a bottom-up optimizer. And the main takeaway to get out of the paper from last class was that once again we saw the importance of keeping track of dependencies between different parts of the query plan and the optimization process to allow us to identify, okay, we know that these tasks are going to be independent, therefore it's safe to run them at the same time. And we'll see this again in today's class again, where we have to figure out, okay, as I'm traversing the tree, I have to know how the data attributes columns are flowing from one object to the next in the query plan, so I can decide when it's safe and when I need to move things around. So and going back to like the system R approach at the very beginning of the class, that was like, okay, I know I got to do these joins, just throw a bunch of, look at all possible permutations and just do the dynamic programming search on them. But it's really a bit more sophisticated than that, where you have to keep track of, here's what's happening in the query plan as I make changes, and here's the task that I'm making, or making those changes for me. And that's going to help me then reason out and figure out what's the next best thing I should do. I can't guarantee that I'll get to the optimal query plan, at least it'll push me in the right direction. And I can do this in a safe manner. If everything's single-threaded, then you don't need to track dependencies to your tasks, but certainly we need to track dependencies between the query plan itself. And as I said, this is the last class was the last one. We'll make this big distinction between bottom-up and top-down, although today's paper, it is a top-down algorithm, right? And I'll contrast this with the bottoms-up algorithm that he proposed 10 years ago, but it's not the same thing as like, are you a transformation-based search or the DP search from the bottom. All right, so today's class, we're going to focus on subqueries. And I don't think I'm really discussing them too much in the intro class. I'm just they say they exist. And you can write them, but now I've got to figure out how we're actually going to optimize them, which is much, much harder, right? So I think since the very beginning, like when SQL was first proposed in the 70s at IBM, there's always been the capability to have nested queries, that you have a select inside of in some part of an insert update delete select state. Which back then you couldn't do selects and inserts. Now you can in some systems. But the idea that you have a select and inside that's another select, and then with an arbitrary number of nesting that allow you to build up more complex queries, that was been around since the 1970s. And you really could put it almost anywhere, right? You can put things projections from where, limit, having, order by clauses can do it, but it doesn't. Like, Postgres lets you do it, but I think it gets ignored, right? And we'll see this in a second. The way to think about a subquery is that it's almost like a function that you can have your query call to get some data you then can use for its purposes, whatever that query needs to use it for. And so again, it's going to allow us to declare within one single query, here's some complex logic we want to compute without having to manually separate the queries, like run the select followed by this select. Like we can kind of send we can send this one giant query, which will be problems for us in a second, to the database server, and have that do all the computation all on the server side without having to send results back to the client, right? So we need to make a distinction about correlated and uncorrelated subqueries, because how you're going to optimize them is going to be way, way different. Of course, correlated ones are hard to do. So uncorrelated subqueries is when you have an inner query that doesn't depend on any attributes or any data or information from the outer calling query, right? So in this case here, I'm doing a select statement, select name from students, where their score is the max score of all the students, right? And the way this will get executed is that the data system can recognize, or the optimizer can recognize, oh, well, there's nothing in this inner query here, the select max score from students, that needs any information or any attributes or any data from the outer query that's calling it. So therefore, I can just run this thing once, like a CTE, materialize it as a temp table, and then now just do a join against that, right? It's super cheap to do, right? And the main takeaway from this is that logically, a database system only has to execute that inner query once. So no matter how many times I'm going to execute it for whatever tuple I'm looking at on the outer query, the result is going to be the same. So logically, you know that this thing can be run once, and then you don't have to run for every single tuple. Now, whether or not the data system is smart enough to recognize that isn't always the case. Like my SQL up until like 5.6 maybe, so maybe like 10 years ago, they would run this inner query for every single tuple from the outer tuple, right? Even though the result would be the same over and over again, right? All right, so again, uncorrelated subqueries, those aren't hard. We can handle those. It's the correlated subqueries that are going to cause problems for us because it's going to rely on, the inner query is going to rely on some attribute, some data from the outer query. And now the context of when this inner query actually is going to get executed is going to matter. Because in this case here, like I'm trying to get the name and the major of the student that has the highest score of all the students in their same major, right? So you think of this outer query, I could run this, I would run this, starting with this, and think of like there's a nested for inside of it where for every single tuple in the outer query here, I want to do some kind of lookup on the inner query, right? So you can start at the beginning, right? Do the name is Jizza, you look at the major comp sci, and then now you're just going to iterate through the entire table doing a special scan to figure out whatever the max score is going to be for the computer science major. In this case here, the score is 90. And then now I come around and do the next tuple, which would be the RZA, right? Same thing. He's a computer science major, so I got to start my scan from the beginning and scan through and find the max score, which is just going to be the same thing with 90 because it's the same major as last time. Come back the third time around. Now we want to do a lookup on UDB. He's the only one majoring in streets. So we start from the scan in the beginning, loop through, and we get the score 100. So this is semantically correct. Like what I just did here, it produces the correct answer, but obviously it's super inefficient because I'm doing a special scan on this the inner query table over and over again. In the case of like the first two tuples, they were both computer science majors, right? The max score was the same. So our high-level goal is to avoid this sort of worst-case scenario where we're stupidly executing the inner query for every single tuple on the outer. And the main takeaway is going to be we're going to try to do this by rewriting things to convert the query into joins. Right? So basically I just said, again, the goal we're trying to do here is again, we're trying to pull out this correlated subquery and then try to be able to rewrite it into a join, which we know how to actually do that efficiently. It's the thing you usually optimize first when you build a database system. So we're going to, in this case here, we put out the inner query as now, and another still an inner query, but now it's being referenced as if it was a table, and like I said, it was a CTE. So now I can run this query once. I'm going to do the max score, but I'm going to group by the major, which again, the group by clause didn't appear in the initial query. And in this case here, also in the inner query, I'm not referencing the outer table anymore. So now it becomes an uncorrelated subquery. So I can run this once, materialize it in temp table S2, then now just keep the join on the outer table, students in the inner table, repeat the group by, right? So this example here, you can kind of squint and say, okay, well, I can figure out the logic by hand when I actually want to do this, right? How to do this rewriting, right? You're doing a join on the quality predicate, right? S2.major equals S1.major. So in that case here, you probably want to use a group by, then that'll just narrow it down. So you're not looking at all possible tuples from the inner table. You're just looking at the whatever group by clause is. The challenge is going to be is that we have arbitrary number unnesting, where we'll see an example later on today, like where a nested query or a nested query can call another nested query, can call another nested query. This can go on technically infinitely in SQL. And how you're now going to be able to identify when it's safe to be rewriting like this and how to do the debugging. That's what today's paper is really about how to take any arbitrary nested query and handle the be able to unnest it in this manner. So I want to talk about real quickly the challenges in just before you can get to the optimizer of how to have binding the query. I know we're not going to the binder. We're assuming that was done upstream after the parser before we get to the optimizer. But it is worth looking at. There's some nuances of how you bind things, and we'll look at some demos where different data sets actually produce different results from nested queries. Then we'll talk about the precursor to the unnesting paper you guys read. Well, how people have been basically trying to do this since like 1980s, like the early 1980s, before everyone was born. Like for the last 40 years, people have been basically using heuristics to try to figure out how to solve this problem, but they wouldn't be able to handle all possible cases. Then we'll talk about the precursor to the paper you guys read earlier. They called the simple duplicate elimination, the simple dependent join elimination, where they were couldn't handle everything, but the basic idea was there. And this is all bottoms up. And then we'll finish off talking about the paper you guys read, which is it's actually not even out yet. The paper comes out next month at the conference, but this is like the leading edge for how to do unnesting correctly. Yeah. Did you read it? Whose name is in it? We'll get to it. Yeah. All right. So binding. Okay. Remember, the idea of binding is you're trying to take references in a SQL statement. After you parse it and you end up with the syntax tree and you have these tokens, and you're trying to map them to objects in the database catalog, right? And then in some cases, if you have a derived attribute, a derived column in your query, now you got to figure out, okay, well, what part of the query plan, what other part of the query is actually producing this result that I can then use for this computation, right? And so for basic things, it can be quite easy, right? In this case here, we know we're scoped inside the inner query here, students as S2. So if I see S2.major, I know where that's coming from, right? Likewise, S1.major, I know where that's coming from. The challenge is that when you have there's different interpretations of what the ordering could be, that's when it becomes problematic. And the really way to think about this is that the subquery is just like a function, as I said, where instead of saying like here's actually the inner select query, it's some subquery or some function I'm invoking that's going to give me back the result and then execute here, right? Underneath the covers, obviously it's a SQL query that needs to get executed. But if you just treat it as like a UDF, right, then now you know that anything that can be passed as an input argument to this function could then be referenced inside of the inner query that's going to get invoked here. So the challenges comes up when you start looking at, again, when things start referencing other parts of the query and it's not clear what is actually what. And the different data systems are going to have different interpretations of what that ordering actually looks like. And so, all right, so for select statements, it's pretty straightforward, any normal column, and then you can also reference anything in an aggregation or group by. In a where clause and group by, it's any all the normal columns coming from your base table, either or intermediate results from a table below you. Having can only access aggregate and group by clauses, order by, anything that can go in here, select can go in there, and then limit. Technically, you can't have any correlated columns. I think in Postgres you can do it, but like it just treats it as returning one. And doesn't actually, but you can't take the output of the tuple and use that as that's the column name I want to join on, or do my limit or order by one. So technically you're not supposed to do this, but like I think Postgres allows you to do it. All right, so let's look at a challenging example where things can be ambiguous. We have a select statement here. We have select. We have an outer query and a select, and then we have this inner query where we're going to create an aggregation without a from clause on this integers table. And then we're just referencing, say, a single column from the integers table that's being referenced in the outer. So there's actually two ways to think about this. Again, if you just think of like the nested query, select sum I1.I, you think that as a subquery, then the question is, like, what is actually being passed in, right? Is it the you're computing aggregation first and then pass that into the subquery, or is the subquery actually going to be doing the aggregation, right? So there's actually two technically correct interpretations of this, and the question is which one it is going to use is going to depend on how it's actually implemented. So let's bring up terminal and play around with this. All right, so I have a real simple table. Connected. One second. All right, so a really simple table. Integers. Right, it has 4 tuples. 1, 2, 3, and then null. So if we take that same query I just had before, run that, you get 6. All right, so what's happening there? Right. Well, Postgres is interpreting this as I'll run this inner query first. It's getting the value of I1.I from the outer table, right? And then as it iterates over that, it computes the sum. Right. So let's go to MySQL. Same query. Right. It produces the single aggregation 6. That's good. Let's go to SQLite. Right. It does 6. That's good. DB. I get 6. That's good. This is what? Oracle. Right. Oracle doesn't like having from clause or selected without froms. So I got to put this fake table dual. Have we covered dual yet before? Right. So it's like a fake table in Oracle. That just has like one attribute with one value, and so anytime you do a query where you're without a from clause, you have to put this dual thing in. Yes, actually, it's 1, 2, 3 null. Okay, so in Oracle, what are nulls in Oracle? You're going to look at Oracle, empty space. And empty string is null in Oracle, right? There's a way to make it fit null, but whatever, right? So what Oracle is doing here is, again, it's taking every single tuple in the integers table, and it's computing the sum on that. Well, what's the sum of 1? 1. What's the sum of 2? 2, right? So what this last one here is null. Is it wrong? Well, it's different than the other ones, but technically, if you just think about it, it's actually correct. It's one way to interpret the inner query, right? So let's do now SQL Server, right? So SQL Server gives you 6. At least now they're also giving you a warning to say like, hey, look, we saw a null in there, and it got removed. So that's kind of convenient. And then let's go to, this is Umbra from the Germans. And this is their, they have an interface you can connect with Postgres, but I'm doing directly to the Mellon terminal, right? Ignore all the stats. What you see is like the sum, it produced 6. So everybody agrees here, except for Oracle. But again, I'm not saying Oracle is wrong, because it's one way to interpret which actually computed. Let's look at another example here. So this query is now in our inner query, we're computing the sum of I plus the sum of I again. But now we're getting the I from the inner table, integers, and I from the outer table. And then now we're then also compute the sum of I again from the outer table and the inner table as well. All right. The question is, people writing queries like this? I mean, yes. This is like the degenerate case. But like, could this occur? Certainly, right? I mean, this whole paper we're reading today was because of machine generated queries, right? All right, so let's go to MySQL. Right, MySQL matches, right? You get 117, 228, 339. They just put nulls first. SQLite 117.228.339, that matches. DuckDB, yep, that matches. Oracle, right? Well, let's try to figure it out. So it's getting 1, 2, 1. So again, the last round was null. It's getting 1, 2, 3 null from the outer integers. Then for the first summation, it's getting that it's just counting. What's the sum of 1? 1. What's the sum of 2? 2. Right? That's fine. And then for this inner guy here, again, because it's interpreting the, I can't highlight. It's interpreting this or binding this, like up here. It's getting this one. No, it's getting this outer one passing from this. So you're getting 1. Yeah, I don't know what that math is done. Yeah. All right, again, it's different. We have to think about that one. All right. SQL Server. So everyone is going to match Postgres here, right? Yep, that matches. Gives you a nice warning again, and then Umbra is going to do same thing here. Right. Let me try one more example here. Right, so here again, we're trying to get now the inner query, select I from integers where I equals the max of the outer query. Okay, so now you got to compute the outer query with that max first, to then be able to use that as input for the inner query. Right, that's a little weird, but it's valid SQL. And in here, there's nothing really to derive from the subplan other than seeing that, from the explain plan, other than it knows that it's getting the max, has to compute that first from the outer table, right? So go to my SQL. My SQL gives 3, that matches. Go to SQLite. SQLite doesn't like aggregates in the where clause. DuckDB should match Postgres. Gives you 3. Oracle. Claim on dual. Yeah. Doesn't like the max in the where clause. And it's surprising that my SQL takes it, because my SQL was originally trying to mimic Oracle's behavior in a lot of way. SQL Server gives 3, and then last one would be Umbra. It gives 3. Right. All right. So Oracle is the odd person down here. There's other examples we could do where my SQL and SQLite start. Especially is that because everyone's trying to mimic Postgres behavior. So what I'd say what Umbra does is probably the correct implementation. It basically has to do how you're going to do the binder. Like in some cases, there's other examples where you could see that if you know it's doing a heuristic-based rewrite, then actually it'll do weird things and produce incorrect results because it's trying to move things around that it shouldn't have. I think all of these examples here is just it's the binder that's deciding when things are how things are looking up. And Oracle does it differently. And again, I'm not trying to say Oracle is wrong, or the second example, the numbers are weird. But in that first example, again, both are technically valid interpretations of that nested query. Just people are Postgres. Everyone seems to be doing the Postgres way. Okay. So, all right. So nested queries can be nasty. How do we actually deal with it in our optimizer? And as I said, since the early 1980s, there's been many proposals about heuristics and rules to do this rewriting. It's basically like the transformation rules we saw in in the top-down stuff, or those rewrite rules we saw in Starburst earlier in the semester, where you're trying to identify patterns where you see, I have an operator that then is calling this operator, and it's it's of this type and it's doing this thing with this kind of data. If I see that pattern, then I know it's safe for me to rewrite things. And so these all have to be written by a human by basically looking at a bunch of nasty subqueries or nested queries, and then figure out, okay, what should I be doing here? Is it safe for me to do? So to give you an example of what these can look like, this is from the documentation of SQLite, and you see they have basically 24 different rules, right? If the subquery is the right operand on the left outer join, then the subquery may not be the join, and the from clause of the subquery may not contain the virtual table, and the outer query may not be an aggregate. Like, these are what the rules that someone would have to write in the optimizer to identify these patterns to then be able to do the rewrite transformation. Again, I'm trying to lift out the nested query to be to be something at the same level as the outer query, so that you can do a join against it, right? So I mean, I'm not picking on SQLite. Pretty much every system except for DuckDB and Umbra Hyper are we doing something very similar to this. So heuristic rules. There was a bunch of approaches in the 1980s, 1990s. In the early 90s, there was now a technique called magic sets. So sometimes when you see, I don't think this paper mentions it, but sometimes in some of the rewrite papers you see for nested queries, they'll mention, oh yeah, you can do this with magic sets. The basic idea of a magic set is it's just rewriting the query such that it's writing into now a table that you can then reference it in a from clause. And in that table, you're adding additional filters that may actually not be in the original query to allow you to narrow down the number of attributes that you're looking at, or number of tuples you're looking at, so that if you end up doing the stupid thing when you do invoke the inner query over and over again, you're not just looking at complete central scan, you're at least putting it down the limit amount of work you have to do. So this work, I think, was invented. Magic sets were invented. Actually, I forget where, in the late 80s. But this is actually what Starburst was doing. They picked this up in the 1990s, and this paper's from this. So this is that example we had before the beginning of this lecture. I'm like, all right, how do I get the student in the major that has the highest grade of all student majors? And my example I showed was rewriting it as a from clause. That's basically what a magic set would do. And again, using the heuristics that we just saw, we mentioned from the last slide, that's how you would identify, like, I can do this as a magic set. And I may, again, add additional things in the where clause here based on how I know the outer query wants to access things, right? Sort of doing predicate push down inside of this. And then what the temp result you're materializing, for whatever reason, they call it a magic set, right? Is it magic? It's a clever name. Like, it stands out, right? Again, the idea is that if you generate the magic set, you can then do a join against. That's me more efficient to do this, to join against this, than doing the dumb thing of iterating from some outer tuple, calling the inner query over and over again. You can also do magic sets with TTEs. You can also just write to a table, a temp table, and then rewrite the query to invoke that. With this simple example here, I'm just doing this as using the first example we had before. I don't want to go too much into what Microsoft does. We'll see this a little bit later on when we talk about UDS. But all the heuristics that are out there, the systems that are using heuristics, they're just probably the most sophisticated. And they have several papers on this technique. But basically, they have a bunch of these rules that you can apply that are orthogonal to each other, independent. And it's sort of like the transformation rules we saw before, where, like, if I can rewrite things from outer join to an inner join, then that unlocks a bunch of additional transformations. It's the same idea for what they try to do. But their whole big thing is that they have this apply operator, sort of like a lateral join, if you remember that from the intro class. We'll see that later on today and later in the semester. But the idea is, again, these apply operators are what's going to be linking things when we have nested queries. And if I can convert these apply operators to inner joins, then I can just do my normal optimization that I had before. Right. So this paper's from 2001. They have 9 rules. There's a follow-up paper I mentioned at the end of this class that they then start doing some of the things that the Germans are doing. on the new version of SQL Server, but that paper actually is not out yet. But they fixed a lot of the things. They try to fix a lot of things that the Thomas did in his 2025 paper that was missed in the 2015. All right, so the main takeaway of this heuristic rewriting stuff, like it's useful. You absolutely want to do it. You can identify probably the most common patterns. You can identify the right way to rewrite them to make things better. But it's really basically impossible to say for any possible scenario, any possible amount of nesting of these subqueries to be able to figure out like when can we rewrite them. Maintaining them is also very difficult too. As I said, like someone's got to sit down and look at all of these queries one by one. It's like, okay, here's what my outline should be here and there. And then it becomes very brittle now because if you change the logic of one transformation, then that may break assumptions that are being used in other transformations. Postgres basically has this problem. Postgres can do some decorrelation of subqueries, but like the optimizer is just a much if then else. And if you break something about you change what the expected output is for one of these rewrite rules, that can break things later down the line. So you can get, I don't want to put a number on it. You can maybe get 75% of the way there using heuristics, but from an engineering perspective, this is not maintainable, sustainable. All right, so as I said, the paper you guys read was the 2025 edition that is coming out next month on this earlier paper that came out in 2015 from the Germans about how to eliminate any possible nested query you have by doing this rewriting the optimizer, rewriting the query plan to convert what are called dependent joins, I'll explain that in a second, into be regular inner joins. And the goal here is that you identify that when you would have to like run a nested for loop to call the inner query over and over again for every tuple in the outer query, if you can recognize that when this occurs and you rewrite it as an inner join, you basically go from an ON to n squared operator implementation, like a nested loop join, to something more efficient like hash join. And it's a significant improvement. And then their claim is in the original paper, but the follow-up paper actually does it, is that for any possible query, any possible amount of nesting, that this approach can handle that. All right, so the first thing they're going to do, one key idea is that they're going to introduce this new operator called a dependent join. This is an extension to relational algebra, where it's a way to represent that there is a dependency between the right-hand side and the left-hand side of that operator, because it corresponds to a correlated subquery, right? And so you just think of this like it's like a cross join, but you're not actually going to execute it as a cross join. It's just a placeholder to keep track of, like, hey, I have a dependent join here. And then again, the whole goal is being able to get rid of these things so that you can then convert everything to inner queries. All right, so say we have this inner query here, and we see that again we're trying to do we're referencing something from the outer query. So there's some filter operator that's going to reference the subquery, right? And again, if we're executing as if it was a nested loop, invoking the inner query for every tuple in the outer query, then this query probably would work. So we want to convert that subquery now into a dependent join, where we can keep track of here's the dependencies that we have for that join. And so for today's class, this side here will be considered the left-hand side, and over there is on the right-hand side. So the right-hand side is going to correspond to what's going to be the inner query, and it's going to have references to things that are on the left-hand side. That's some part of the outer query. All right, so now here we have this filter clause on the right-hand side, which again is referencing something from the outer query. So again, we're doing this comparison between the student major in the outer query and the student major that actually is on the inner query here, right? So we need to understand how can we rewrite this part over here to not again have to do the dumb invocation of the inner query for every single of the outer query. So the dependent join is just it's a relational algebra. It's going to keep track of the correlated subquery, and the way it would be implemented again just blindly was for every single tuple on the right-hand side, we got to join it with something on the left-hand side. And so it's just a way to keep track of, like, here's a dependent join here. I know I want to remove it. And so the goal is going to be to try to push it down to the bottom of the right-hand side and then convert it to a regular join. In some cases, just eliminate it entirely. So then now the placeholder join here would just become an inner join. So conceptually, that's the high-level news. And so the algorithm, this first implementation, is going to go from the bottom, find the first dependent join it sees from the bottom going to the top, and then rewrite that and keep going until it gets to the very top of the query plan. And I know I don't have any more dependent joins. And then the paper you guys read is going to do in the opposite direction and actually look at multiple dependent joins at the same time. All right, so the way we want to rewrite this now is that, again, we want to push down this dependent join on the right-hand side, and we'll do this sort of step by step as we go down until we get it near the bottom, right? So the dependent join is going in this direction. So we're going to then target this filter here because we know this is actually the join clause that we're going to care about, right? So we're going to add a join up here, and that's just going to be looking at the major from the scan operator from the student table, and then it's going to look at the major that's coming out of this dependent join down below. So going back here, we sort of swapped we moved the dependent join down by one, and then the filter operator came to the top and then converted it into an inner join. We still have the filter down below over here. All right, now we introduce this new operator as well, called the duplicate elimination scan. And all of this is going to be is a sort of special type of scan that basically has a distinct clause that's going to guarantee that the tuples coming out of it will be distinct. And we need to be able to do this because we, if as we're doing the scan here on the students here, like if somebody doesn't have a major, it may not get produced as part of the output of the scan here in the aggregation. But this at least guarantee that like something will come out of it. So we still capture every single record that's in the scan, right? So again, we're trying to do this again without the semantics are the same, even though the physical plan is changing as we go along. Okay. All right, so think of the duplicate scan as like a select query where the projection is the same as whatever's been grouped by list, just guaranteeing that things are coming out without any duplicates. All right, so now we're going to keep pushing down this dependent join as far down as we can as possible. So in this next step here, we're going to move it down by one and move the aggregation to be above the dependent join. And so because this is duplicate elimination scan is attached to the dependent join, it's going to come down with us like this, right? So again, now the aggregation is above. We have a dependent join. We have a duplicate elimination scan, and that's just going to be tied up with the scan of the student table. Another thing to point out too is now because we know we're doing a join on the major coming out of this side of the tree, the right-hand side. Now we can actually also introduce a group by clause on the major. And this guarantees that we're not going to have duplicate majors coming out of this, which reduces the amount of the tools we have to look at when we do our join. Again, same thing. Keep going, push the dependent join down further. So now we're going to swap places with this filter. That's going to go above. The duplicate elimination scan is going to come down below, and the dependent join moves down. Right? All right, so this is good. Now we're at the bottom, right? And so we can't go any lower because it's a join between the scan table and then the special duplicate elimination scan. So the dependent join is basically the same as a cross join, just has a special marker that says I'm a dependent join. Right? You could implement this as a cross join with a special flag and say, hey, I'm a dependent join. But to keep clean, you just have sort of separate distinct operators. So then now that we have we're at the bottom, we convert the dependent join into a cross join, which again is still semantically correct because this will do the join above us to remove any duplicates we don't need. But now, if we have a filter above a cross join, going back to system R or Starburst, we know that this could be converted into an inner join, right? And then these guys slide up. All right, now this is a lot better. Right, we got rid of our cross join. The filter is built into the join operator. Right. And then now we can remove the duplication scan entirely because we know that the group by clause is going to remove duplicates for us as well. So then this part here just gets rewritten now to be the scan on students. And then at this point here, we have to then convert the filter with the inner join, filter and the join into now inner join, where now I can take the output of the aggregate from the max score and do that in my join in my inner join up there.
I think the reasoning of the paper is slightly different. So obviously the aggregate will duplicate small lines of first D is duplicate 3. We know that the value of most 1.1.
What's our number of rings? Oh, sorry. Say it again.
The reasoning is slightly different. So
About what step? This step here? Or this step?
Yeah.
Here.
This part.
Yes. So the paper says what?
It says this works because D will duplicate 3. Thus we know that when join find at most one join partner and reverse original dependent join is transformed into the relational algebra notation, and then thus the join condition can be enforced at this point in time. So if it's saying D is duplicate 3.
I mean, like this?
Are you saying yeah. This is a unique D is a unique. I don't know like the nature.
Yeah.
Yes, I'm saying that the nature is unique, and then only one thing that is matching. So
It's like per student has one major. Yes.
that's why
It's like a one-to-one correspondence. So in this case here, you know that coming out of this, the
you only need to look at it.
So his point is here, like the join clause here is D major equals S2 major, right? So it's not matching students. So this is basically kind of doing a Cartesian product of like for every student in the same major, match it up with every other student in the same major, right? And that's unnecessary because you're just gonna collapse it down on the aggregation here. So you're saying we don't look at this aggregation up above? Okay. Regardless, like as long as you understand, like everyone understands, like the flow is happening here, right? So going back to the very beginning. So we started back up here, right? We had this dependent join where there was this filter down below that was trying to reference something on the left-hand side, and so I'm going to try to push this down so that this thing percolates up, and then now I'm just scanning scanning the table on the left-hand side, computing the result that I need, and being able to pass that up to this joint and then place up here, again, without having to re-execute that right-hand side query for every single table on the left-hand side. So going back here, right, so now I'm going to do my join. I'm going to match up on major here. Dependent joins here. This is just making sure that I see everyone that I expect to see. And then sort of like almost like a left-out join. And then now this is doing the aggregation I need for the score, right? So then now when I push this down further, right, aggregation goes above. I add the group by here because I know that's the thing I'm going to join up above. And I don't care about every single student in a major. All I care about, again, whatever the max score is for me. So the group by guarantees that I'm passing along the minimum information I need up to do this join. So then now it's just pushing this thing down further. And here now I recognize that, okay, I'm going to reference the major. Sorry, I know that I need to just pass along the major in order to do the group by here. So now when I rewrite something, put the filter up above, that just becomes then an inner join after I get rid of the cross join. And then now at this point here, I'm doing a join where I'm getting sort of like a mini cross product for every student in the same major, matching up with all of the students in the same major. But I don't need that. So therefore, it's safe for me to go ahead and remove the duplicate scan and just do the scan on itself. And there's a logic you can keep track of. What access do I actually need to come out of this? And therefore, if there's something I don't need with this combination of the join operation that I don't need, then I can go ahead and eliminate that. He's nodding yes. Everyone is staring blank. Okay. I mean, does everyone not understand this? Because it gets worse. What? Well, sure. Okay. So there's a version of shared here. As I said, when the paper came out in 2015, it didn't actually get a lot of attention because he published it in this thing called BTW, which is like the German only database conference. I've spoken there. They invited me there. It's the best of the Germans, not just the Germans in Munich. Otherwise, but like, it's not Sigma, it's not VODB. But regardless, this paper got picked up by a couple of people. Dr. Eagle re-implemented this. I know my student Databricks, she implemented part of this, not everything. I don't know of any other system that does this, like that people would actually use. But the challenge would be that, like, if you now have nested queries with nested queries, that's when this approach actually is going to fall apart, because it can only examine one dependent join and try to eliminate that one at a time. And it may end up producing an inefficient query plan, because it'll remove one dependent join, and then it goes and tries to move to the next one. And actually, if you knew about both of them at the same time, there are other additional optimizations you can do, right? So as you read the paper, you probably saw this get mentioned where, like, oh yeah, somebody named Sam Arch was sent us a bunch of queries where things didn't work, and that led to him writing this paper. Well, Sam is the #1 PhD student in CMU, right? This is an older photo of him, but like this is my student upstairs on my floor. He's the one that found problems with this approach and sent Thomas an email. And so this is the query he sent him. Obviously, you can't read this, but like I'll just do it in one piece. And so it's lateral joins calling lateral joins calling lateral joins. So this query is actually being generated by a computer program using a technique or a thing called the program called Pilot called AppFell. Basically takes UDFs that you're calling from a SQL query and then converts them into, in this case here, lateral joins. They have a newer version that can convert things using CTEs. But instead of having like a UDF call, like thing like PL SQL, and calling that as if it's like a black box, you basically rewrite the inline now SQL inside of the problem query. Then now you fill out the optimizer and it knows how to reason about it instead of doing poorly estimating what the UDF is actually going to do. All right. We'll have a whole class on this. The paper you guys read will produce in SQL Server, and then we use the apply operator I mentioned before. But in this implementation, it's using lateral. So you can see, like, it's a nested query calling a nested query calling a nested query calling a nested query, right? And this falls apart in Umbra at the time. So here's a reduced version of the query that I just showed you. And the thing I want to point out is where does the technique fall apart? Right, so we have two dependent joins. We have this one at the top here, and one at the top, the one in the middle here. And again, this join operator with the shaded side and the open side, that's the sign for dependent. All right, so then we have this dependent join here, where now we have it's referencing things from on the left hand side here. So in the first pass, using that algorithm that I showed you, it would go ahead and try to rewrite this piece here, right? Get rid of the dependent join, rewrite everything down here. But then now, it would then try to say, okay, now I got to get rid of the second dependent join, and you end up with this more convoluted query where you see, the output of T1 being fed into all different parts of the system, and it basically claims that, I think the error they were hitting, it was running out of memory. Umbra couldn't compute this inefficient query for it. And a big part is that there's cross joins in here where it actually isn't going to get, they're all going to get filtered away, but because it has to materialize the animated results going up, it just wastes a bunch of time computing things that are unnecessary. So the other thing I want to point out too is what's important to this, and that's necessary for the technique about to see, is notice that this query plan is actually not a tree like we normally show in the intro class and maybe a bunch of the queries we looked at this semester, right? It's actually a DAG. Right? I can take the output of one operator here, and that's being fed as input to other operators. Most systems don't represent their query plans as DAGs. Most of them use trees. In Umbra, and in DuckDB, and in Hyper, and our own thing we're trying to build here, we want to represent these DAGs since it can allow you to know where things are being fed into it. You want to reuse computation, in different parts of the query program. That's actually one of the key things that make this all work. All right, so the paper you guys read was the 2025 edition of the duplicate elimination, the dependent join elimination algorithm that I just showed. And the key difference here is that, again, that 2015 version was going bottom to the top, doing removing one dependent join at a time. And this one they call holistic unnesting, where you're going to basically do a pass on the query plan first, figure out where all your dependent joins are, and then now work from the top to the bottom and try to eliminate them. And in some cases, if a dependent join has another dependent join below it, it may end up getting eliminated before you get to that second dependent join. Or if you keep going down and you see that second dependent join or third or fourth, then now we can then reason about how to combine them all at once together. Right? So again, you do sort of two phases. The first phase, you go through and figure out where all the dependent joins are, keep track of how the data is being moved between the different operators. And then the second phase is then going to the top and bottom and rewriting it. So one of the things the paper talks about is that you want your optimizer to be able to find the things that understand where the data is being moved between one operator to the next, and understand the dependencies between them. So that's what I'm saying in the beginning, like you need to know dependencies between the tasks. In this case here, now I need to know the dependencies between the operators, where data is actually being generated from, and where is it going. So they mentioned that they have this thing called their indexed algebra. And this is basically a additional data structure that the optimizer is going to maintain internally that keeps track of what operators are generating what attributes, and then what other operators in that query plan are actually using those attributes. So they have this notion of what they call a source operator, and it's just saying for the base tables that I have, my base relations, or if there's a projection that we use for that computation, here's where they're actually coming from. So in this case here, A is going to generate X, Y, Z, B will generate X, and then C will generate Y, Z, D. And so IU just means information unit. It's a way to describe the scalar values that are coming out of those these operators here. And then they have this also notion of consumers. Or actually, yeah, so you would have it for both the base tables and then for the additional operators in the query plan. And then they have this notion of the IU consumers, and that's just keeping track of like, okay, for the IUs that an operator generates, what other operators in the query plan are actually going to use them. And the reason why you want all this additional metadata is as I'm going down and trying to do that rewriting of my query plan, removing those dependent joins, I want to know if I move an operator above or below, start moving its location, are there other operators in some of that subtree or other part of the query plan that actually depend on the result that my operator is generating, and therefore I know when I'm allowed to move these. So in this case here, like A produces X, Y, Z, and you can see where A.X, A.Y, A.Z are being referenced. And you would have the same consumer connections for everyone else. Right? So again, before you start doing any optimization, we just have the initial logical plan. We'll do a pass over this, generate this additional data structure, and then they'll keep referencing it later on when they actually do optimization. All right, okay, so first pass, we're going to do identification, right? So we want to identify all dependent joins we have, and then we want to determine whether we think we can use the basic algorithm that I showed before and just rewrite it, or do I need to do something more complicated? So they're trying to compute, again, what's called the lowest common ancestor for every single operator to know whether that data is being generated by something below it that is allowed to swap with or not, right? So going here, starting this guy here, this first dependent join, right? You identify, okay, well, I know I need to do do a lookup on TA, or T1, T2A, or T2A on my left-hand side is going to come from this operator 6 down here. And then I'm also going to need to reference, the T1.A is being referenced by this guy over here, right? So that's problematic because I'm accessing something on this side, but I know it's coming from over here on the other side, right? And then also need to access T1.A on this other side here, and that's coming from the same source here. So in this case here, for this dependent join at the top, 1, I need to know about where the data I need is coming from operator 6 and operator 9 down below. In the case of T5, and we only care about the left-hand side. So in the case here, the left-hand side is accessing T1.A, and that's being generated by something on the right-hand side of the query plan, so the left-hand side of the query plan, and therefore I got to keep track of that. I care about that. I don't care about this one here because again, this is on the left-hand side. I only care about whatever's on my right-hand side. Like the operators that I'm accessing. And then now you sort of see this idea that I can identify where things are, what attributes these operators referencing, because I have that index algebra. It tells me, I would have this link to say I'm accessing T1.A, and I know it's coming over here. And then you would know also that T1.A is coming from the parent of parent of this operator up above on its left-hand side. So it's my left-hand side implicitly. And therefore, I know I got to figure out how to resolve that later on. All right, so now again, I'm just doing a quick inspection to say, all my operators are accessing, all the operators access the left-hand side of the dependent join. And then if it's simplistic, meaning like I don't have if my dependencies can easily map to the other side and I can pull things up, we showed before, then I go ahead and just run that same algorithm we had before, right? Otherwise, then I had to start doing this recursive rewriting going down from the first dependent join and just do that same thing where I'm trying to move things up and switch things around so that I end up decorrelating any of my references. So the example they give is pretty, it's pretty explanatory, but like it's a pretty big jump at the end because it's the same query plan, and then all of a sudden, okay, here it is, we get it. I'll try to walk through what they're actually doing. All right, so again, we have to deal with these two dependent joins, and because we're going to be going from the top to the bottom, we're going to first start with the one at the top, right? So the full holistic plan, the idea is that we're going to try to rewrite on the right-hand side all dependent joins, so that there's no references what we call the outer side of the operator. The outer side is just going to be the things where like it's referenced on the left-hand side, right? And then we're going to keep track of the state of where we're at as we're going down. To me, this is being run as a single thread, where I know what level I am on the query plan. I know how I got there as I traverse down. I know any dependencies that could occur across those operators as I'm going down. And then that's how I identify when it's safe for me to go ahead and do the rewriting. So let's start at the very beginning, right? So here's that same query plan we just saw. And then now we have this, starting with join 1 at the top. And then now we have the state information here. So the outer reference is telling us that there's something on the right-hand side of this operator that we're starting with here that is coming from the left-hand side. So T1.A, which is being referenced here and also here, that's coming from over there. So that's the thing we got to deal with. The C classes thing is like equivalent columns, and they use this for transitive reasoning. So it's things like if I have like A equals B and B equals C, then I can replace that reference to C with A, if it's available to me, which I would know because I have that index out. So this allows me to be able to identify that I'm accessing something that is going to be on my left-hand side, but I know it's actually can be mapped to something that I already have on my right-hand side, so therefore I can remove that dependency. And then the RPR is just a mapping from the outer ref columns to any new column that we generate. Now, this example I don't think touches that. And then this here, the next is just telling us as we traverse down, what's the next operator we want to examine here. So in this case here, for this this aggregation on operator 4, we know that we traverse down and try to handle that. And then just keep track of it in the stack as we go down. So now that we're at this operator here, right? Nothing changed on our outer reference because we're still accessing T1A at this point. There's no equivalence classes. The RPR thing, we ignore that. And so the only thing we identify here is that, well, we know when we want to keep going down because at this point here, we just have this aggregation. There's not enough for us to be able to do any rewriting to get rid of that dependent join 1 at the top here. So this is saying that at this point here, we got to keep going down. So then we land here. Now we end up with another dependent join, right? And so this one now has references on its left-hand side and right-hand side to things that are on the left-hand side of the dependent join at the top, which we're keeping track of the stack as we're going down. So we know we just can't do, again, simple elimination. So we're going to have to keep traversing down and go further to find what we can rewrite. And now we see what we have in our equivalent classes. We are aware that T1.A is going to be equivalent to T2.A because we have this equality predicate here. And therefore, we know we would have a match at this point. So we can substitute things as needed. So again, now in this case here, now we're going to go to the left-hand side and look at this projection operator. I'm sorry, the filter operator, because now I'm looking at T1.A, T1.A. And so I'll go here and then keep going down and try to figure out when it's safe for me to start rewriting. So at this point here, we haven't done all we've done is just maintain some state information about what we're seeing as we're going down. But we haven't made any modifications to the query front yet. All right, so now we're here, and this is just a filter, so we know we're going to have to keep going down, and then we end up with the scan on the base table T2 here. Equivalence class is the same, the outer reference is the same, and again, our stack is just telling us what we're doing as we're going down. So now this is the first amount of rewriting we're doing, and this is again in the example, we go moving from this to this. So let me try to explain what's happening here. So we have this this part of the original query plan got rewritten into this part here. So we still have the filter on T2.A.T1.A. Now we have this join clause where that's telling us we're scanning T2, but now we're also getting a data actually from T1 here. So because again we're a DAG, we know that we can connect T1 from this part of the query plan, and that its information can then be fed up into for us to do this join here. Not determining what order actually I'm going to do any of these joins. Just logically, I know that the data I need to be able to do the join to T2.A and T1.A, that's now going to be able to come from this thing over here. Right? So at this point here, we still have dependent joins though, but now we have a way to get the data we need for an outer reference to T1.A. Now we have a way to link it in and get it into us, right? So then now we got to come down to the other side of this dependent join and rewrite this piece here, right? This is doing an aggregation and then coming out of a filter, which then a scan on T3. Again, this was another big jump occurs. So what's happening here now is that we kept this scan of T1 feeding up to this join here. And then now we kept the scan on T3, but now we're able to map over these dependent joins into regular joins, because everything that we need to do the computation that we need for dependent joins is now available to us. And here, because of the equivalence classes, instead of saying T3.A equals T1.A, because we know that T1.A is equal to T3.A, because we're referencing that in our join, then we just substituted in that filter here to say T3.A equals T3.A, which then we stripped out because it's unnecessary. So that's a way to get the transitive clause allows us to say we can get data from this part of the query plan here without even having to connect it, because we know we're due up above the equivalence check on T3.A and T1.A, and therefore I can push that down and eliminate that need to get that data over there. And then the top, so that gives you that gets rid of the join 5, this dependent join here going across. The aggregation still stays the same, but now I think we're grouping Y on T3.A, similar to what we saw before. And then up above now, we're getting the same count greater than 5 clause for the join, but as well as now matching T1.A and T3.A. I think it's correct. There's obviously a big leap here of how like they don't explain later on like this part here is sort of magical that you can say, oh yeah, T1.A comes T3.A. And I sort of get that. How this part here though got connected without blowing it up and becoming a and how would you actually then be able to execute this as you're spitting out tuples? You need to feed this and then also feed this one above. Like I don't know whether this path gets eliminated or not. Logically, I think this makes sense, but actually, the devil's in the details. So the question is, how do you maintain this thing? How and when? What do you mean? Yes, so the question is, when are these things being updated? As you go down, then this is getting updated. And then you basically look at whatever operator you're looking at, and then you look at that index, the index they're maintaining, to tell you what they actually feed here, right? So, for example, like he's missing the step here, like T1.A becomes T3.A. You would get that from this, but he doesn't show that, right? Because that's the big trick, to remove that dependency, like this edge to this edge. That goes away because you can recognize from the logic we've seen over here that I'm going to do a lookup on T2.A. That's going to match T1.A. And then I can push that up to do T1.A equals T3.A, but I got T1 because I joined it with T2. And therefore I know that match is going to happen here too. Like that's the magic part. I don't know how he's doing that. And like I said, it's a pretty big leap of going from from this figure into this figure. How that all works is not really clear. Other questions? This question is like it's this one here, right? The top one I can kind of see because it's similar to one we had before, right? Like you're pushing up the filter and that becomes at the top. This one here is the magic. This T, the join 5 here, right? Because you're rewriting on the other side. You're not spanning out what this join is. Start pushing up clauses that you had over here, and then the C class is he's got the algorithm. I guess one could implement it. And I mean, in the back of the paper too, he has also he has rules how to do the rewriting for more complicated things like cursive TTs and stuff like that. I forget whether these specific examples have the exact algorithm instructions. The high level thing what you get from this is like, okay, like one that you can do this, right? And whether you can actually implement the algorithm based on my presentation is unlikely, which should not be likely. But you could take that paper and understand, okay, this is what it's trying to achieve, and then actually go ahead and be. And again, there is an extra piece that I didn't mention about they are making decisions of this connection piece here, which is actually a cost-based lookup, where there's two different choices of what you could do. And they're hand-wringing on that, but like the first algorithm I showed you can do without a cost model. This one, you would actually pull out a cost model. then make better decisions about how you want to actually rewrite this. But I'm just going to ignore that for now. I mean, this is super hard. It's not a non-trivial algorithm. But as long as you understand the high level that like I can start from the top, go to the bottom, and rewrite things based on I mean, it's similar to the patterns that we saw, but like for the heuristics, but it's more like here's the methodology to go forward and look at the the operators, decide how things are being moved around, and when is it safe for me to go ahead and do them. And I'm doing that at the low level, the sort of algebra level, where those heuristic rewrite rules are sort of looking at a higher level operator. Like, do I see an inner join followed by this? Therefore, it's go ahead, safe for me to rewrite. So the first demonstration I showed of the unnesting from the 2015 version, that was showing it at sort of the operator level. The heuristic rules would be the same way. He's doing this at the low level algebra. Okay, so I think this is state-of-the-art approach. It just came out. Only Umbra implements this, but this is the definitive way to do this. I think. Again, you need to have your query plan be a DAG, otherwise you can't do the connections he's doing. And then it's not required to have the index algebra, but that'll definitely speed up the traversing and identifying the connections between different operators if you have that supplemental data structure that they maintain. So we're going to see these nasty correlated subqueries again. Again, lecture after the midterm. Sorry, after the spring break, because we'll see this again with UDF inlining. Because again, that was the motivation for why he ended up writing something. So side comment, and I'll bleep this out. All right, again, so like this is super challenging. Very few systems that can implement this. It's Umbra and Hyper. Umbra is state of the art. DuckDB can do some of these things as well because, again, going back to Sam, he sent patches of DuckDB when he took 7.1 2 years ago, because they were trying to do this UDF inlining thing, and DuckDB couldn't handle lateral clients. So DuckDB does more of the Umbra paper, not the new one, but the old one, because of we sent them patches. But this is considered the state of the art. All right, so next class, we're going to start talking about next section of the semester. We're talking about cost models, and this is the dirty secret is going to be all the things we talked about so far. Like, oh, great, we do parallel searches, we can do efficient join enumeration. All of this is going to fall apart and come down crashing because our cost models are going to be terrible. And this is not just anyone said everyone's going to be terrible at this. So we'll understand the basics of it, and then we'll see where things go wrong. And then actually after the midterm, after the spring break, we'll actually look at adaptive techniques where you actually try to learn when your cost models go wrong, try to get feedback from that, try to correct things and get better. Right? Sort of like a reinforcement learning technique. But we have to start with the basic cost models, use statistics, and then cardinal estimations, and then we'll pick up again after the spring break. Okay?
We're gonna go with Brownie. Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Get one, Big Al, Mike Strokes, Drumley, I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep your Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like a make them hoes fuck quick and suck dick. Crown me as the thugs in the gun. Shit, some niggas claiming never rapping and sudden. Don't push the button, yes you motherfuckers in front and you don't want nothing. If it did, it'll big start something.